So I also want to briefly mention factor analysis. It's not as widely used as principal component analysis in natural and environmental sciences. It's more of a social sciences analysis, but it's a fine analysis. You can definitely consider it. It's very closely related to principal component analysis with just a small twist. So I explain it really as a follow-up or alternative to the principal component analysis, and you need to watch those previous videos in order to understand what I'm talking about here. So if you haven't done that yet, work your way through Unit 2 first and through the Lab 2 first, and then this is just a follow-up or alternative, and you will immediately understand what it does, building on the principal component analysis. So another multivariate technique that's related to principal component analysis is factor analysis. And I want to briefly illustrate to you how that relates to principal component analysis. And for that, I have a slightly modified US arrests data set, just so that we actually have two factors that we can look at. So it's the same data set as before, almost. So this one is manually entered here. I just loaded that from a CSV. I'll give you a download link for this one at the end of the video. So it does have the same values here, murder, assault, rape, and urban population that we talked about before. But I also added an income level here, and that's related to the urban population. And the reason I did this is because I wanted two factors that we can discover here. So these are somewhat related. That's how I created this data set. So now this one we have to prepare a little bit because it's not a built-in data set. We have to define the row names. So I'm going to do this here. So my row names are going to be the state, and then I get rid of that first column here, which is the state itself. So if we look at the data set now, it's actually just row names, and we can feed it into the principal component analysis just as we've done it before. So if we do this here, let's run this one and take a look at a biplot. So virtually identical to what you've seen before, except now we have two vectors here, right? So urban population and income, they're both related, and murder, assault, and rape. The other ones we already said, this kind of is a crime factor, and maybe this one is some sort of, I don't know, this is an urbanization factor, or we can call this a development factor. So here you have high urbanization, lots of jobs, high income, and so on. So we can actually see this already in principal component analysis, that these are orthogonal to each other and that they don't have anything to do with each other. But what factor analysis does is it does give my rotation a little bit of a twist, so that the component 1 and the component 2 represent those factors. So the crime factor and the development factor, that they are as parallel as possible to these components. It's just a small twist of the coordinate system. So we can try this out here. So, but before we do this, let's just take a quick look at our summary statistics here for the principal component analysis. So we have 52 and 35% of the variance explained by those components. And because I want to compare this with the factor analysis, I'm also calculating this manually. So here, based on the eigenvector, those are my eigenvectors, and if we divide the eigenvectors by the number of variables, so number of columns in my data set, that's 5 variables that I have here, 1, 2, 3, 4, 5. So if I divide one by the other, this is my variance explained. So I just save this here in that object variance explained, and you can see those numbers are identical. So manually calculated and what the software gives me. Okay, now let's move on to factor analysis. As I said, this one does a slight rotation to maximize the concordance of the components with my vectors. A common one is a varimax rotation that does this. And I do want my scores, so I want to do a plot and see how it looks like. So you have to actually specify this manually. So we do this via regression. So principal components are actually just linear combinations of the original variable. So very easy to get those scores. It's basically a multiple regression. So let's run this one here. So that's my factor analysis. And we look at the plot of the first and second score. So in this case, I say type n, so I don't get the points. So this is just a blank plot, and then I put the names of the states on here. So there they are. And now I'm going to use vector fit command to put the vectors back on. We covered this before. And you can see now those vectors are better aligned with my factors. So my rape, assault, and murder are as aligned as good as can be with factor 1. And my urban population and income is aligned as good as possible with factor 2. So that can be useful. If you now look at your loadings, my correlations with my factors are actually very high, right? Urban population and income 0.98 and 0.91. So those values have been maximized. So if I do those varimax rotations, one of the rules of thumb is that whatever is larger than 0.4, you can think about an underlying factor to those components. So if we cut this off here at 0.4, then you see murder, assault, and rape goes into my factor 1, and urban population and income goes into my factor 2. So that's a very nice summary. These variables, factor 1 and factor 2, you could now relabel with a new name. So something like crime and urbanization or development or something like that. So while I maximized my correlations with the original variables, one of the things that suffers a little bit here is the variance explained. So those are now 0.42 and 0.38. And if we compare this with the principal component analysis that where we saved this earlier, so those values were 0.52, so 0.1 less variance explained, and factor 2 has a slightly higher value, so it's 0.38 instead of 0.35, but it can compensate for the overall variance explained. So my PCA is the optimal solution if I want to have the maximum of the variance explained in the first components, and my factor analysis maximizes those correlations and compromises a bit on the variance explained. So both are fine. Usually in natural and environmental science, you don't see factor analysis applied very often, so we just usually stick with PCA and we make that small rotation in our heads. But if it makes sense, there's no reason why we shouldn't use this as well here in natural and life sciences if it can simplify things nicely. Good. There's a whole bunch of other things that you can look up in this output file. So I just want to give you some examples here. There's a uniqueness score, and you can see the most unique variable here, so the one that scores highest, is rape. So this one is actually one that is not highly correlated with any other. So urban population and income, they are replaceable by each other. So they score low, they probably belong to an underlying factor, and murder and assault also are reasonably low, so they belong clearly to a factor. The one that fits in least is the rape component. So that one is shorter, so it doesn't score particularly high with either factor 1 or factor 2. It actually scores higher in factor 3. So that could be an independent dimension yet. So if you wanted to look at one more factor, that's the one that I would look at. So that would give you another dimension that you can think of sticking out toward you on the z-axis here. If you twist this whole coordinate system to the side, which states would score higher in rape. But it's only a very small percentage that is additionally explained there. And we can also look at the correlation table, so this is nothing particularly exciting, but it just shows us also which variables are correlated with simple correlation coefficients. So urban population and income are highly correlated with 0.89, and assault and murder 0.8. And if I look at murder and rape, it's actually only moderately strongly correlated, 0.56. Good, so now you also know what factor analysis is and how it works. So this is mostly it for factor analysis and principal component analysis. The one thing that may be worth mentioning is that you can view those factors and principal components also as linear combinations of the original data. So that's a bit of an advanced application for power users. If you want to skip over this in the lab, you certainly can. But For those who are interested, that's an interesting property, and you can use it. So let's remind ourselves what we have here. We have our factor analysis scores, or those can also be principal component scores. So I abbreviate them as FAS here, so that my code is a little shorter, and we can look at them and we know they are. So these are simply the coordinates of where my states are located. So for example, Wyoming will be at minus 0.1 and something like minus 0.3 for factor 1 and factor 2. And our original variables, these are similar coordinates, and those apply to these axes, right? So you remember this is a kind of a rotated cube in a multivariate space, and it's projected onto this plane described by my two factors here. But those are in a way also coordinates where these individual states sit in that multidimensional cube that's projected onto a plane. So since it's just a projection, those factors here are just linear combinations of the original variables. So I can express them as a linear model here, and this is essentially a simple linear regression. So I have my factor score here as a function of my original variables. That's a simple multivariate regression. And so if I execute this and look at my summary here, we'll see that we got coefficients, so that's essentially the formula, and we got a perfect R square. We even got a warning message here, essentially perfect fit. Summary may be unreliable. So if that was real data, that would be a cause for concern. So that's too good to be true. But in this case, it's exactly what we expect. So it's just a rotation. There's a perfect relationship between the variables and your components with an R square of 1. And so let's do this also for our second component. So now we have two models, two formulas that we can use to predict factor 1 and factor 2 from original data. And that's actually very handy. If you collect additional data, you can just plot that into your factor analysis or principal component analysis. So let's pretend that there's a made-up data set. We had our first US arrests data set from 2000, and now we did the survey again in 2020, and we want to see what has changed over time. So let's bring this data set in. It's got exactly the same format, except it says now different numbers. So everything has changed a little bit. And we want to plot it on here. So in that case, we have to calculate the scores from the original variables, and we have the functions for that. So we can just use the predict function here, using the formula that's in the object on the new data. So let's see how that works. And now we are ready to put these new data on here, and I do this with the arrow command. So we don't have to do the plot because it's still here. So I can just execute the arrow command. So I'm drawing arrows from the original coordinates here. So these are my original coordinates for each state for factor 1 and factor 2, and we want to see where they went. So that's the new coordinates for 2020. So I'm adding those factors as arrows that are blue and that have a tip length of 0.1, so that looks a little better than accepting the defaults. So let's execute this, and we now also see how each of the states has developed over time. So there's an enormous amount of information in this plot now. First of all, we have a multivariate ordination of a bunch of variables nicely sorted so that my x and y axis represent different factors. And then we also see how each individual state has developed over time. So for example, we can see that Connecticut has one of the longest vectors, so their crime statistics in this direction have improved significantly, and their urbanization and economic statistics have also improved. And so if I look at this as a whole, I would say for the richer states, we generally have improvements, and the poorer states, they tend to get poorer, but their crime statistics are actually kind of mixed. So sometimes they go to the right, sometimes they go to the left. So there are no real trends there. So a lot of information summarized in a single graph. So that's an awesome simplification of a very complex data set and trends over time, everything in one. So that's what you're aiming for when trying to make complex data sets digestible. So if you want to try this out, I just added a small mini lab, part B, on factor analysis. So this is not a standalone unit, but you can just try out this twist to principal component analysis with this lab and the data set.